We're going to talk about exponential growth. Uh, Also could be exponential decay, but we're going to go through some exponential growth examples. All of the homework problems are on exponential growth. Decay is basically the same process, so we're just going to go through this one side of it. So we can find an exponential model of any base. We like to use base E because it will model very well any population, even the human population. So the exponential growth model and decay model will make use of an exponential function with base e. It will be raised to a power that involves the relative growth rate, usually denoted by small k. And it's the rate of population growth expressed as a proportion of the population at any time. So, for instance, if the growth rate k is 0.02, then at any time t, the growth rate is 2% of the population at time t. A population experiences exponential growth according to this model. Y equals Y naught. The little sub-zero is called naught, N-A-U-G-H-T. Y equals Y naught times E raised to the power of K times T. Y, this Y right here, is the current population. It's the population at time t. So this is the current population. Y naught is the initial population. K is the growth rate, and T is the time. If we are in decay, if the population is in decline, K will be a negative value. If not, if it's in growth, if it's increasing, K will be a positive value. So let's work an example and we'll get an idea for exponential growth and decay. The initial bacterium count in a culture is 500. Initial, that's initial population. That's Y naught. So Y naught equals 500. A biologist later makes a sample count of bacteria in the culture and finds that the relative growth rate is 40% per hour. Now that tells us a lot of information. The relative growth rate is K. We always give K as a decimal value, not as a percent value. So you're going to need to turn percents into decimals. We know 40% is 0.4. Per hour tells us that we're going to give our time, t, is going to be in hours. So A, find a function that models the number of bacteria after t hours. So we want to come up with an initial population exponential growth function that's going to model these bacteria for any time t. We know Y naught is 500, we know K is 0.4, so we've already figured that out from the setup of the problem. Then it says, what's the estimated count after 10 hours? So we'll use the model to answer that question. When is a time question. This is asking for time. When will the bacteria count reach 80,000? So when will the current population, that's Y, at what time will Y equal 80,000? And then it says to sketch the graph of the function. I don't think we'll take time to sketch the graph, but we'll definitely answer the first three parts of the problem. So we're going to use the exponential growth model. Again, we know Y naught is 500. We know K is 0.4. So Y equals Y naught e to the K times T. So we've substituted in for Y naught. We've substituted in for the growth rate K. And we know that t is measured in hours. So that answers A. There's our model that's going to help us answer any question they might ask us about this particular population of bacteria. Part B said, using the function, find the bacterium count after 10 hours. Well, 10 hours is time, so we're going to substitute that in for t. We know time is measured in hours, so we don't have to change, 10 days into how many ever hours. It's direct one-to-one units here, so we just substitute in 10 for t. And so now we have Y equals 500 e to the 0.4 times 10, or e to the fourth. Our calculator tells us that's 27,300. Let me make a note here about discrete data versus continuous data. You're lots of times, if you turn this into a number, if you put this in your calculator, you're going to get a decimal answer. And you have to understand, if you're talking about a population of deer or bears or wolves or moose or bacteria or whatever it is, this is discrete data. There's one whole moose, there's one whole bacteria. If we had said that this was 27,300.543, we don't round that up to 27,301. That's not true. We don't do the regular rounding thing with our decimals. We always do what they call truncate. We actually cut off at the decimal and don't count anything of any value after the decimal in this context of a problem, because we have to have whole individuals in our population. So part C says, at what time will the current population be 80,000? So we know that's Y. We're going to substitute that into our model for Y. We divide both sides here by 500. That's where we got the 160 from. And then we're going to introduce natural log to both sides, just like we do when solving these exponential equations. We know the natural log of E to the 0.04t, natural log in E, undo each other. They're inverse operations, so we're just left with the exponential expression. And then we have t equals the natural log of 160 divided by 0.4. You can put that into your calculator if you would like to, or that is a perfectly well-defined real number answer. If you find yourself on a quiz or an exam and you don't have your calculator, giving your answer in these terms is perfectly fine. If you do have your calculator and it makes more sense to you to talk about 12.68 hours, 12.7 hours, that's fine. Time is something that we can approximate. We can have a decimal point on. You know, we can talk about having 12.7 hours. We can't talk about having 12.7 bacteria. So just use your head, use your brain, and know when you have to truncate or when you have to round. So let's work another example. It says the graph below shows the growth of Mexico City metropolitan area from 1970 through 2000. In 1970, the population of Mexico City was 9.4 million. By 1990, 20 years later, it had grown to 20.2 million. They want us to find the exponential growth function that models the data, and by what year will the population reach 40 million? So let's see what we know about what's going on here. Let's talk about initial population, time, all that kind of stuff. This tells us in 1970, our initial population was 9.4 million. So in 1970, we're going to say t equals 0. That's time. So t equals 0 in 1970, and our initial population was 9.4 million. We know that 20 years later, when t equals 20, if we're measuring t in years, then the current population in 1990 was 20.2 million. That information right there is going to allow us to find the growth rate. That's going to allow us to find K. And this is what we see most often in exponential growth and decay problems, word problems. They'll give you two sets of data in the initial setup of the question. They'll say, you know, in this year, this is what the population was. And then later in this year, here's what the population was. We find this often, and that is specifically for us to solve for K. There's really nothing else we can do with that information. We're going to use that to solve for K, and I'll show you how we do that. And then they'll ask us a second question. So this question might say, in 1970, initial population was 9.4. 1990, it had grown to 20.2 million. In what year will it reach 40 million? So that's what a typical question would look like. So let's see how we go about answering this. We know we're going to use the exponential growth model. It's a population of humans. It's what we use to model growth in populations of humans or anything living for that matter. So just like we said before, t in 1970 would equal 0. and at the time there were 9.4 million inhabitants. So there is just our general exponential growth model. Y equals 9.4. This is going to be in millions. E to the k times t. Now we need to find k, and we're going to use that other information they gave us to find k. So we're given that there were 20.2 million inhabitants in 1990, so we know when t equals 20, y equals 20.2. So we're going to substitute that information in here and see how brilliant that is, because that takes care of every variable in our equation. They gave us a value for y, they gave us a value for y naught, they gave us a value for t, so the only variable we have left is k. So now we're going to just solve this for k. We're going to divide both sides by 9.4. And then we're going to take the natural log of both sides, and that leaves us with 20k equals, and then we can use our calculator and find the value for k. So now we actually have the growth rate, and we have a well-defined model for this specific situation. We know that y naught is 9.4. We know that k for this particular problem, no matter how many things they ask us about it, or how many years they want us to use, or how many different pieces of information they give us, for this setup, k will always be 0.038, because the growth rate of this population is never going to change. So remember, they'll give you a word problem. It'll have two basic sets of information. You use those two sets of information to find the value of k. Once you find the value of k, you then have the model that you're going to use to answer the actual question that they're after. And here's the actual question that they wanted. They want to know, in what year will the population grow to 40 million? So when will y equal 40? When will the current population? We're looking for the time that the current population will equal 40. So we substitute in 40 for y, divide both sides by 9.4, take the natural log of both sides, and now we're just going to solve for t. So here we're talking about whole years, so the 0.109 is not useful for us. We'll drop it, and so 38 years beyond the initial setup of 1970 will be 2008. So it says the model indicates that the population of Mexico City will reach 40 million by 2008. So there's just a straightforward, really generic exponential growth problem. In the previous example, we solved for t. We're always going to solve for k. That's in every problem. But sometimes they'll ask us for y. Sometimes they'll ask us for t. Using the exponential growth, we can find k with the first set of information that they give us. And then when we determine what the actual equation is for that population, then we can answer questions whether they're asking about y or y naught or t. So come to class next time. We'll work some exponential growth word problems. See you in class.